Okay, morning. It's a good pleasure to have Leonardo Lessa as our speaker today. Leo is a PhD student at Perimeter Institute, and he has done a lot of interesting work at the interface between quantum matter and quantum information. In particular, in recent years, he has discovered a lot of interesting interplay between symmetries and entanglement, not only just in pure state, but mostly in mixed states, which are kind of surprising. And today he's telling us more about this story, decohered but still entangled.
Yeah, thanks so much for introduction, Liu Jun. And first of all, it's really a great pleasure to talk here in this amazing seminar series. So yes, I'm going to tell a little story about how symmetries and anomalies can constrain mixed states. So they are decohered but still entangled. All right, so the outline of the talk will be two to three parts. So first, we're going to talk about topologically ordered mixed states, viewed as states with these one-form anomalies, mainly in two dimensions. Then I'm going to move on to talk about global zero-form symmetries, and if time permits, I'll say some things about what happens if you don't have an anomaly, but you still have some interesting things happening there. Okay, so first of all, just some basic things about symmetries and anomalies. So they are among the most useful non-perturbative tools to study quantum many-body physics, right? Usually we have these states over many bodies, and they're usually very hard to study. You resort to perturbative arguments or numerics. But if you know the symmetries, if you know the symmetries have anomalies, then you immediately know some useful properties about your state. Symmetries by themselves, as you all know, are ubiquitous. They're, for example, part of the Landau-Ginzburg paradigm of spontaneous symmetry breaking. They can protect topological phases in SPTs. And even topologically ordered states can be viewed as coming from higher form symmetries. Anomalies, on their hand, they still have similar properties, and there are many ways of defining anomaly and different perspectives from field theory to lattice systems. And I got to really talk about the equivalences between them because it's a delicate topic. But for us, the only thing that matters is that it has a property about symmetries that guarantees that their symmetric states are non-trivial in some way. Hey, later on, I'm gonna use that in a well-defined way that's gonna be clear. But what it means to be non-trivial, well, it can mean many things. It can be gapless, topologically ordered, SSP. But something that encompasses all of these possibilities is long-range entanglement. So my basic question here is, can we generalize this property of anomalies implying long-range entanglement to mixed states? And our mixed states here, I mean states described when you have incomplete knowledge of your system. A lot of times when your system interacts with an environment. All right, so firstly, topologically ordered systems. And so what I'm going to talk about is based on this work with Shen Ti, Peter, Tim, and Trong. And see also all these other works who talk about similar things. So as a motivation, topological systems, apart from their interesting properties in theory, they're also becoming increasingly more useful for quantum computation. Both in, I'd say, like two ways. I guess on the left is an example of how surface codes, the Tori code, for example, can be used as a quantum error correction code, right? And now you're seeing these quantum platforms actually having very interesting results using these states as quantum error correction codes. And on the right, you see another application, which is just to produce these states on the quantum devices. And recently, we can even go for non-abelian topological order. Right, and which is a common feature among these topologically ordered states is that they are robust to perturbations. And well, if your perturbation is strong enough, at some point you're going to lose, for example, the ability to have a quantum memory, right? And this has been known for a long time. This is one of the first like fundamental papers on that. And the idea is that if you vary your error strength, you give this parameter p, then there's some PC, this threshold, above which you cannot decode the information back that you encode in your topologically ordered state. Right. But okay, so one of my goals here, I guess sub-goals, is to view this decodability transition, so the ability to decode information in this topologically ordered state, as an actual phase transition, as we're mostly used to in condensed matter systems, but not for mixed states. And these different phases are going to be characterized by having different higher form symmetries. Okay, so there are many concepts here that need to be explained. So first of all, let me talk about symmetries in mixed states. So the usual textbook definition of a symmetry acted on a mixed state is what I will call the weak or average symmetry. It's just by conjugation. So symmetry element G here, let's say unitary. If you conjugate mixed state rho gives the same state back, then you say it has a weak symmetry. And that is equivalent to you being able to write rho as an ensemble, so a mixture of different probability weights of states. They are symmetric. They might have different charges, so this alpha I here indicating the charge of these states, but they're still symmetric. But for our purposes, that's too weak. Why? Well, because even the maximally mixed state, they still have no knowledge of the system, is already weakly symmetric, right? You just conjugate to get identity back. But we want some way of defining symmetry such that it already guarantees some useful property about your state. So that's why we go for the strong symmetries, or also called exact symmetries, which algebraically you can imagine your symmetry operator G only acts with the left multiplication, and you get the state back with some phase factor. And it turns out that this is equivalent for the state rho to be a mixture of states with the same charge alpha here. Okay, so it is a stronger condition. You can imagine that these states can arise, for example, if you have a system that, let's say, already starts with some symmetry charge sector, and then it can interact with the bath, so you can lose information about your system and become mixed, and you can exchange energy information, but it doesn't exchange charge. So charge of your system itself keeps constant, right? So at the end, you're gonna get a state that it still has strong symmetry. Okay, what very useful property of strong symmetries that you're going to use is that it inherits a lot of the times. So one inheritance property is that if you write a row as any ensemble, any mixture of any other density matrix rho I in any way, if rho itself has strong symmetry, then each of these states also have strong symmetry if this probability is positive. And also if you have an extension of rho, so actually this rho comes from a rho tilde in an enlarged Hilbert space, so that you trace out this ancillary Hilbert space here, H prime, then this extension also has the strong symmetry, but now the strong symmetry only acts on the Hilbert space of rho. So the idea is that strong symmetry is very strong. Okay, having talked about how symmetries act on mixed states, let me now discuss definition of a phase for mixed states. So, I mean, the main definitions for phases, even for pure states, but the one I'm going to use is motivated by this quasi-adiabatic continuation between phases, right? So I guess one definition is that let's say you want to talk about ground states or Hamiltonians, right? And you can say, oh, say the Hamiltonians are in the same phase. You can connect two of them such that the gap, like if they're gapped, the gap doesn't close. Then we know that because I had a better continuation, that the ground states are connected via unitaries, they are local, right? Which for me, I'm going to approximate by these finite depth quantum circuits. And the idea is to generalize this definition for mixed states. But now I have two-way connectivity in a sense that I go from, say, from rho to sigma via local channel, and also from sigma to rho via possibly another channel. And what I mean with the local channel here, well, it's the following: is any channel of this form that is written here. So when you act on a state rho, you append first rho with an ancillary state in a trivial state, let's say all zeros, right? Then you act with a local unitary on this enlarged space, and then you trace out the ancilla here. Right, so it's basically a local unitary, but acting on this enlarged space. So this I'm going to call a local channel. It is local in the sense that it preserves the locality properties of a state. And here there could be two different channels because a channel is in general not invertible, right? Although actually the only invertible channels in general are the unitaries. For unitaries, if you know one way, you also know the other, but for channels, you don't have that. And that's going to be important.
Question?
So Yes?
Here is this definition of a local channel the same as saying the cross operators are all local?
Good question. Um, yes, it is. Yeah, so this is equivalent to saying that there exists a decomposition of a channel in some cross operators where each cross is, let's say, is a basically a local circuit. Yes.
Mhm. Thanks.
Yeah. Yeah, thank you for the question. Um, okay, so now we can define a phase, at least abstractly, as just the equivalence class under these two-way connectivities. But, well, you can totally define that and look at its properties. However, these local channels, they cannot produce long-range classical correlations. So that say the state where it's just zero product state trivial is not in the same phase as its classical SSP state, which is a mixture of all up and all down. Well, that's just because the state in the SSP state has long-range correlations, but the above state doesn't have. But to be able to look at this from symmetries and topological order, we want to say something about long-range entanglement and not just any type of correlation. So you're going to change the set of my set of my operations that define the phase to be able to construct these long-range correlations. So the change is going to be for these so-called stochastic local channels, where I change this trivial state in the ancilla, 0 here, with any state that is classically correlated, so an arbitrary classically correlated state. So I start with that ancilla, and then I apply some counter operations that are local. Right, so now I'll call two states to be in the same long-range entanglement phase. We're going to drop out the long-range entanglement when I say if they are two-way connected via these stochastic local channels. The operational
Uh,
meaning of this,
Sorry. So I'm a bit confused. Uh, so in this definition, do we have to fix, first of all, what does it mean to be classically correlated?
right, yeah, right, yes. So more specifically, I mean the following. Um, you first choose an on-site basis, right? Let's say Z basis, and then your row C is just a mixture of states that are diagonal in these on-site bases.
I see. Then the right-hand side of this equation depends on row C. That's so so this ESLC rule is just something that depends on the choice of row C.
Exactly, yeah. Yes. So the data that defines the stochastic local channel is both now the local unitary and this arbitrary
Uh-huh.
correlated ancilla. Yeah. Maybe there's another picture I'm going to say now. Maybe it's going to be clarify a little bit more.
Mhm.
So like an operationally motivated way to understand these guys is suppose in the lab you have access to two local channels, we're going to call EU and ET for up and down. And now you flip a coin. If it goes up or heads, then some probability P, you apply this EU. Some probability 1 minus P, you apply the E down. Right. This mixture of channels, which is the actual stochastic process that you apply, is a stochastic local channel. You can basically have this probabilistic mixture in the channels and input that into this classical ancilla. So these two definitions are the same. Um, Consequently, these trivial states, so the states that are connected, two-way connected to a product state, are exactly of this form. They are mixtures of SRA states, right? So in the literature, I guess is kind of like the most general Schrodinger entangled states that one wants to have for mixed states.
Neil,
So now, mhm.
can you explain again the motivation you mentioned on the right side of this slide? You said, uh, yeah, local channels cannot produce noise correlations. Then, what is the motivation to use this new definition again?
Right, yes. So the motivation is now I want to trivialize long-range classical correlations. I basically want to include any, instead of say this state here with all up and all down, I want to call this trivial. Why? Because, for example, it will become clear later, but I basically want to say that the Tory code and like other mixed states that I see the Tory code phase, for example, are long-range entangled and not just correlated.
Uh-huh.
Uh,
But what is the precise definition of classical correlation?
right, yeah. So yeah, that's a very good point. So if you have an arbitrary state, you cannot just disentangle. It needs to be quantum classical. I guess what I can say is that there are states which I would just call definitely just classically correlated, so no entanglement, which, for example, are these ones here are just mixtures of states in a single basis, right? Uh,
Uh-huh. And
yeah, I
also
guess
like
that's the only thing I can say, I guess, in principle.
and also like the GHC state in the above is also viewed as just classically correlated but not non entangled.
Exactly, exactly. Yeah, so it is of this form here. Yeah,
I
this
see.
mixture of Schrödinger entangled states.
Thanks.
Yeah, thank you. Yeah.
Wait. Then let me make sure.
Mhm.
Maybe suppose I consider the pure GSC state. Do you consider that as long-range entangled or short-range entangled?
There will be long range entangled. Yeah. Oh yeah,
Uh-huh.
something I didn't mention, but we want our definitions for phase equivalence for mixed states to somehow match definitions for pure states. It turns out that this one does match up to like let's say something called catalysts. But yeah, basically it matches the pure state classification. So if JTZ, for example, is long range entangled in a pure state sense, it will also be in this sense.
Okay. Thanks.
Yes. Yeah. Thanks. All right. Yeah. If there's any more questions, and please ask if you do have. Right. So now let me join these two. So now I'm going to argue that the strong symmetries can be pulled back along these stochastic local channels of the trivial ancilla. What I mean by that, so suppose I define this group G rho, which is a group of the strong symmetries of state rho. Then I'll argue now that if sigma is this some stochastic local channel acting on rho, so rho goes to sigma via this E, then um, you can pull back the symmetries of sigma, this group G sigma, via some operation to strong symmetries in rho. Okay. You see this, for example, for local unitaries, that is very simple. You just conjugate the symmetry. But this would be some kind of conjugation. More precisely, this is what I want to say. So suppose you have here a stochastic local channel, and so then there exists local unitary U and some ancillary system A, such that for any state of rho, I have this mapping here. So this would going to be a mapping from E acting on rho, so this G sigma here, to the G of rho times an ancilla. Okay, so in this picture here, I'm not writing ancilla, but you have some ancillary state. And it's defined the following. So for any strong symmetry G of my output state, so E of rho, I define this dressing of a G. So I first actually append an ancilla with an identity acting trivially there, and then I dress it. And it turns out that this is a strong symmetry of this guy of rho, tensor, and ancillary state. And also in such a way that preserves the strongest charge. So if E of rho has some charge, the distressing there's a rho times the zero state is also going to have the same charge. Moreover, you can take U to be a dilated local unitary of any of these local channels in the ensemble. I'm not going to show the proof, but it's basically this idea of dressing symmetries in the Heisenberg picture, but then you dilate it to an ancillary state. And actually, I'm gonna not write down this ancillary state, also because I'm gonna use this to talk about long-range entanglement, and appending an ancilla that is trivial is not gonna change the long-range entanglement property. So right, so the picture we have here is, for example, suppose imagine some section of this high-dimensional phase space of states. So by definition, two states, rho and rho prime, are the same phase if they are two-way connected by these stochastic local channels. And then so there's the strong symmetry group are basically the same. You have pullbacks going both ways. But if you have, for example, sigma, there's another phase, it might happen, for example, that you can go one way, say from rho prime to sigma via this f, but not the other. It might happen you can't do both, but it might happen you can just do one way. Then by this inclusion of f star, you can just include a group of strong symmetries of sigma into rho prime. And I guess the upshot of all of that is that phases of matter defined in this sense are dictated by their strong symmetries. It's something that is invariant on the whole phase in this sense. Right, now I'm gonna pivot to talking about anomaly of one-form symmetries. So I'm just gonna focus on abelian topological order in 2 dimensions. And there, the topological data is basically just braiding in the self-statistics of the anyons. More specifically, now if you imagine, for example, on the left here is braiding, how I define braiding? If I have these Wilson lines that create the anyons, right, it's anion red here A and then blue B, then braiding just means that locally where they cross, I just change the order operations. If when I do that, I get just some phase vector, this SAB, then I'll say that these 2 anyons braid with this phase vector SAB. Right, so I just change your operations here. Here's a picture where these 2 one-form symmetries are also like dressed, maybe already dressed operators. And similarly, I can define self-statistics. So now self-statistics is a little bit more difficult to define. Basically, I want to define something that does exchange. And the way I define is that if I have this anion A here, if I have 2 lines and they come intersect at a point P, and afterwards they go in the same path. And if I change the order of these 2 paths, if I pick up a phase, this phase here will be the self-statistics. So for example, if it's a fermion, this operation will get you a minus sign. Turns out that this is equivalent to, if you know the T diagram, that exchange that basically moves the anion in 2 different ways where their difference is an exchange of their positions. Okay, why I define like this? Basically because I want something that it's only talking about how symmetry acts locally. Sorry, yeah.
The question is, given WA and WB, are you assuming here SAB and theta A are phases?
Assuming there are phases.
In general, I'm looking at
Sorry.
the commutation between 2 unitary operators.
Right.
They in general differ by a unitary operator instead of simply a phase.
Right, exactly. Yeah. So I'm defining when it happens that if I change, say, these order operations, if the difference is just a phase, then I'll call this braiding. So I guess I'm just kind of by definition limiting myself.
Okay. I think
And of course,
it would be useful to have a way to extract the phase, meaning there's a way to design how they cross and cancel all the non-universal part and make the result just the phase. This is possible.
right.
This is possible.
I'm not sure if I just too much, maybe you mean something that's actually on the next slide. So yeah, let me postpone a little bit that, then we can discuss. But for now, just assume that if it so happens that the difference is a phase, call this braiding. As if a
Sorry,
toric in
Leo.
the end is just X.
Leo, I have a question. What about the triple braiding of the strings?
You mean if you have 3 strings intersecting at the same point?
No, like the chromium ring.
Oh, right. Yeah. So for Bowman ring, for example, then to produce such a diagram, I would just look at one of the intersections and do this operation. So yeah, so I guess this picture is basically just looking locally at when these lines intersect. You can do other things like outside. You can do other things.
Is your statement that you're considering only one-form symmetries in which the triple braiding can be expressed in terms of these local double braidings?
Exactly. Yeah, exactly. I think so.
But I don't think that's a generic thing, right? You need to pick like a very special topological order, I think.
Oh,
I
I
think
see. I
it's
actually,
yeah, I think that's independent data in general, but yeah, like I think you can certainly like build um like the triple braiding from the double braiding, but that's like I don't think that's generic. Yeah.
yeah, interesting. Actually, I didn't know about that. But so he just talk about a billion topological order. Does that happen also for
Yeah.
just a billion?
Yeah.
I see.
Yeah.
Wait, Hank, I'm a bit confused.
Yeah.
For a billion topological order, self-statistics and the fusion completely determines the topological order. Why do you need additional data?
Isn't that for 1 + 1D?
I'm talking about 2 + 1D.
No, your statement is for like annuals, right?
Yeah, for 2 + 1D, a billion topological order, fusion rules and
Yeah.
self-statistics completely determine the topological order.
Yeah, but that's for annuals. That's not for strings. I think Leo's talking about strings, right?
Yeah.
By saying completely determining the topological order, even the strings are determined. Or we can also think of it from another perspective. All the abelian topological orders can be described by some K-matrix transcendence theory. And knowing the K-matrix in the transcendence theory enables us to calculate any type of braiding of any Wilson loops, meaning the strings. So I don't think for a abelian topological order there's any additional data.
Yeah, also let me just say that I'm not in the business of classifying topological order. I guess I'm just saying, okay, when this happens, okay, then there's this phase I can use.
Okay.
Yeah. Sorry, was that a question?
Maybe not.
No.
Okay. Yeah. Okay. Maybe yeah, I will continue. Okay. And similarly, so strong symmetries can be pulled back, but also the anomaly is invariant under this symmetry pullback. And the reason is similar to the pure state case because what you're doing when you're pulling back these symmetries to other states in the same phase is that you're just dressing the symmetries up to something trivial and ancilla. Right? So for example, if I have this one form symmetry here, this W of gamma, at times an identity that I'm not showing, if I just conjugate it, its gates are going to cancel out everywhere else that is just far from this with some less, so just get some dressing. And in such a way that because I define these braiding and self-statistics to be something about when just local property when they cross, then this dress just cancels itself and I get the same phases back. Right? So anomaly is invariant similar to symmetry pullback. And now, okay, so for I guess a punchline of all that is that I will prove that if you have a state with this anomaly, then the state is bipartite entangled. Given that, an invariance of the anomaly, the symmetry pullback, immediately tells us that it's long-range bipartite entangled. So first for the proof of bipartite entanglement, the proof goes by contradiction. Not giving every detail of here. Actually, I'm going to give similar proofs of more detail later. But the idea is that, okay, let's assume that there is a state that is symmetric and anomalous symmetry. It is also separable. So it's a tensor product of two things of A and B. This A and B is like these half planes. Then I consider two higher form symmetries here with non-trivial braiding, this gamma and tau. And because the state is separable, also the symmetries can be separated. So just this gamma acting only on region A or only on region B, and same thing for tau, these guys, they are open, are also symmetries of my state. But then this becomes a contradiction because I'm opening now these string lines, but they're still symmetries. So in fact, if I consider the product of the two, they're gonna change by a phase when I change the order of operation, right? But they're both symmetries of the same eigenvalue, so that gives trivial braiding, which is a contradiction if you assume you have a non-trivial topologically ordered state. Right. So these states are bipartite entangled, but not only that, but they are long-range bipartite entangled because so what I mean by a long-range bipartite entanglement for mixed states, it means that not only I cannot write rho as an ensemble of tensor products, but also if I act with a stochastic local channel, I can also not do that. And why is that? Well, also by contradiction. Let's assume that you have a state rho with this anomalous strong symmetry of this form. Then I can pull back this strong symmetry and get this strong symmetry dressed is a symmetry of just this ensemble. Then I can use the inheritance properties of the strong symmetry and get there is a symmetry, a strong symmetry of each of these parts here. And then I just piggyback to this proof here that I just told you. So this
So here strong symmetry refers to strong one-form symmetry.
exactly strong one-form symmetry. Yeah.
Also, let's make sure in the leftmost side of the picture, if I just look at the upper half or look at the lower half, that's just looking at half breeding, right? In general, this half breeding is not unambiguous, it's ambiguous. I guess the argument is really something like the product of the upper half and the lower half together is generates some non-trivial phrase SAB. So even if for the lower half, the phrase is one, the upper half cannot be one. Is it right?
Right. So if I understood correctly, you're saying like, okay, so there exists some ambiguity on how I open these strings. Is that right? Like at the
How you open the
endpoints, there's some
string,
ambiguity.
how you open the strings, yeah, and also inside the string, like in this figure, the blue and the red, they may still commute even if the closed loops don't commute, right? Or are you,
Right. Yeah, exactly. The closed loops, I'm assuming they commute, right? In this sense. Um, But
I see.
now I cut these symmetries and I make them cross at a point that it is far from this boundary. I can do that. So there's no like ambiguity on what I do when I open these strings. So this crossing here, the difference between these two guys was exactly correspond to this phase factor
Mm.
being my definition.
Okay. Yeah, thanks.
Yeah, that's the idea. So yeah, thanks. Right. And yeah, one thing I want to remark is that I'm not assuming anything about a state on A and B individually. In particular, the states on A and B, they could be like hard random, volume law entangled, any state in a Hilbert space, any mixed state in a Hilbert space. And you can if you use by this proof, you can still not their mixture is still not topologically ordered in this sense. All right. One way to quantify this long-range entanglement, as customary for pure states, is using this so-called topological entanglement entropy. One way to calculate it is by considering this Levy-Wayne tripartition. So you consider A, B, C regions of an annulus inside the bulk of the system. A and C are separated by B in this way. And now if you compute the conditional mutual information between A and C given B, turns out that this gives something about the topological data, which is the log of the total quantum dimension, which is from here the sum over dimensions of each anion squared. So we define a similar quantity, also based on this work here by Turing and others, which we call the topological integral formation. We take the so-called mixed convex roof construction, which is so I have this quantity here, which is works well for pure states. And now given a mixed state rho, I minimize over all the possible decompositions of rho in some probabilities P and rho I. And then given this decomposition, I take the average with this probability distribution P of the decomposition of the topological entanglement entropy of each state rho I. Right, so I just take a minimization of all possible decompositions. So of course, it's something hard to calculate, but it's well defined. And it turns out that we proved that there is a lower bound to this topological entanglement formation for any state with these strong anomalous symmetries. And the formula is this one is lower bound by half log n, where this n is 1 plus the number of non-transparent strong symmetry anions. Non-transparent here means that there exists some non-trivial braiding with another strong symmetry anion. A strong symmetry anion here just means the symmetry, the Wolfram symmetry. Yeah.
So this N is just the total number of anions.
Yes, with this caveat of the non-transparent anions. Yes.
I mean, if we are talking about bosonic topological order, there's only one transparent anion, right? So one plus non-transparent is the total number.
Exactly. So yeah, so that's a very important difference between pure topological order and mixed topological order. So for pure, I least believe that, or at least or believe or is defined by modularity condition that you have no transparent anion except for the trivial one. But for mixed topological order, you can have like transparent anion. So there is, for example, this mixed topological order. I'm not gonna talk about that, although it's very interesting. So it happens if you decohere the toric code and the ZX phase, not just Z and X, but ZX at the same time, you get a mixed topological order given just by the trivial anion and the F anion. So you do have some non-trivial self-statistics of the F, but it's transparent. And the claim is that it is still a non-trivial phase, even though you only have this 1 and F anions.
I see. And the reason this can happen is because it's not a pure state.
Exactly. Yeah.
Uh-huh.
So people call this as intrinsically mixed phase because of that.
I see. And this definition reduces to the previous one if it's pure.
Is that which definition you mean?
The topological entanglement of formation reduces.
Oh, right. Yes. Yeah, it does reduce. Yeah. Yes. Yeah. Very good. Very good. So if my total state is pure, then there's just one decomposition. One, which is the trivial one. It's just psi equals psi. So this minimization becomes just over one term. Exactly.
So it also suffers from the spurious contribution.
Yes. Very good. Very good. Exactly. It also suffers from problems for spurious contributions. Yes.
Thanks.
Nice. So, for example, for toric code, F, E, M, and F anions are non-transparent. So 1 plus 3 is equal to 4. You have this lower bound. And now the interesting thing is that this lower bound is valid for this entire mixed state phase of matter that contains the toric code. The proof is actually pretty much a generalization of the pure state proof of such bound, given these two papers here. Especially this one by Michael Levin, which reviews this proof itself. With the only caveat, I guess if you know the argument, but I guess the idea of the proof basically is that you consider this annulus here, and then you start creating anions inside the whole of this annulus using the weak symmetries. So now you consider this WB prime here with there's an open string. You create the anions inside, and now you're going to have different mixed states, right? That differ by this action of this weak symmetry. And you prove that on ABC, these mixed states are orthogonal. And when you can detect this anion you're creating via this strong symmetry line that goes around the hole, by detecting if they had non-trivial braiding, then each anion that you can distinguish contributes a piece for this conditional mutual information. So you can lower bound by that. That's basically the idea of the proof here. Right, and I guess just to mention, if you have a strong symmetry, you also have a weak symmetry. So in this case, you use both to create and detect the anions. Right. So let's apply what we have now for the case of noisy toric code. So the setup here is we have the toric code Hamiltonian, the usual, the start terms, and the Plaquette terms. The toric code ground state, well, I guess one of the ground states is a position over all loops, let's say in the Z basis, and it's long-range entangled. So this state here is at the lower, is at this point here, the lower bottom of this diagram. And now I consider acting with some decoherence noise on this state. So the coherence it has two parameters, px and pz. And for each qubit at each edge of the toric code, I active these channels where I decohere x and equate z in this way. So probability 1 minus p, I do nothing. Probability p, I conjugate by x or z. Right, and the phase diagram you get is this here. I'm gonna kind of motivate why is that true. So the goal here is to motivate why you have this toric code phase. Close to toric code with the topological interval information here constantly being log 2, and a short range attainment phase here, topological information equals 0. So, okay, but before that, let's just go to another fixed point that is easily describable, which is if you have total z dephasing, so right up here in the z-axis, then you get a state which we want to call the loop state, which is the mixture of all loops, the z basis. Basically, you get rid of all the off-diagonal terms. You just have the diagonal part of the density matrix. And it's a short-range entangled state under our definition. Why? Because it is the mixture of product states, which is these loop states here in the z basis. Right. So at some point, you must transition between long-range order and short-range order, and long-range entanglement to short-range entanglement. And a very useful tool to analyze where this happens and to prove this two-way connectivity is this paper by Shen-Chi and Tim. It proves stability of these mixed-state phases under limb-bodied evolution if you maintain the finite Markov length. So this finite Markov length is a length scale defined in this following way. You consider this tripartition A, B, and C, where in this ring format. And now you compute the collision mutual information between A and C given B. If that decays with the distance, that is radius of B, exponentially, then this sigma here is your collision length is called the Markov length. And the idea is that if you let's see, look at the picture here. If you evolve your state rho 0 the limb-bodied evolution, and you know that the Markov length stays order 1, then you can they actually produce a way to go back or another limb-bodied evolution. So usually, sometimes, so I guess in this whole diagram, we know how to go from toric code to any of these points, but it's usually a very hard problem to go back. But it turns out that you can just compute this Markov length, and if it still remains finite, you can't go back. So there's something you can just compute for these models, for this phase diagram specifically, and you find that it just diverges on these two lines here, right? So in principle, there could be 4 different phases defined by these 4 different regions where it doesn't diverge. But okay, here we definitely know is a toric code phase. And for these rectangular regions, we also know is the same phase as short-range entangled phase because, for example, one of the states here is short-range entangled. So it's the same phase as trivial one, so the entire phase is also short-range entangled. Turns out that in other work, so the difference between this region here and this region is that this region, rectangular one, has classical memory, and this one has no memory. But the way I defined these channels, stochastic local channels, they are not, they don't detect the difference. So they just distinguish between the quantum memory and the classical memory, and classical or trivial memory. You can also calculate the topological information for these two, and it's basically using the lower bound that we have. So we know from the argument I just told you that in this phase is lower bound by log 2, and this phase is lower bound by 0. And then you find a particular decomposition, and this was done in a paper by Teruno and Yishue, the square root of row decomposition. I'm going to go into details. But with a particular decomposition, you can upper bound the topological interval information because it's the minimum over all decompositions of this quantity, right? So if a particular decomposition can upper bound, and then with both upper and lower bounds, one can get that it looks like that. Okay, if there's no other questions, so the summary of this part. So I define mixed phases of long-range entanglement, and they are characterized by strong symmetries. They are pulled back with this framework of symmetry pullback. The strong anomalous one-form symmetries imply long-range bipartite entanglement of the states. And I can have this lower bound to this topological interval information, which is a generalization of a topological entanglement entropy to mixed states.
Question?
Mm-hmm.
In the case of pure states, the lower bound of topological entanglement entropy is a lower bound. I mean, it's an inequality only because of the spurious contribution, meaning genetically that inequality is an equality. Is this also the case here?
Because in many cases, the inequality is an equality.
In the generic case, this inequality is an equality.
You mean like it is like fixed point, like case of topological order? Is that what you have in mind?
I would like to phrase it as saying this gamma f is larger than the right-hand side only if there's the spurious contribution.
Right. Yeah. So I guess one thing you can say, for example, in this phase diagram, there is exactly log 2 for Toycode phase and exactly 0 for showing entangled phase. So for these guys, it's for this phase diagram. We can calculate exactly. It does match what we believe. Maybe you're asking like, how can we have spurious contributions? Sorry, I'm not sure if you understood the question.
Yeah, basically, for the case of pure states, the topological entanglement entropy is really, in most cases, is just the log of quantum dimension.
Right.
And only if there's some spurious contribution is larger than that. Here I'm
Right.
asking, suppose I consider the phase diagram. Is there only just a measure zero subset of the phase diagram where this gamma f is larger than 1/2 log n? And in almost everywhere is equal to that.
Yeah, that I'm not sure. I guess it would be, as I said, like for pure states, this TEF reduces to a TE, so it is as hard of a problem as just for the case of pure states. So I guess like, okay, how actually I'm not sure like how generic is pureness.
Mm-hmm.
I'm not sure. But I guess it's already a difficult question for pure states.
Mm-hmm. Yeah, thanks.
Yeah, no, thank you. All right, so with that, I'll move on to the second part. Let's talk about zero form anomalies. So this is based on this work with Monchang and Chong. And okay, so right now, the logic that was presented for like by long-range bipartite entanglement is that you prove bipartite entanglement, you prove invariance and the symmetry pullback, and immediately you have this long-range bipartite entanglement for the case of one-form anomalies in 2D, so topological order as we know and love. Now I'm gonna extend that to zero-form anomaly, so global symmetry anomaly in, let's say, 1D for first. Now, what I'm going to prove is tripartite entanglement. So by definition, it is, so I say it's tripartite entangled if it's not written as a mixture over tensor product over 3 regions, A, B, and C, right? And with same thing, the same idea, you can prove long-range tripartite entanglement. And I'm also gonna, extend this to other higher form dimensions, and now you're gonna have more D+2 partite entanglement if I'm in D spatial dimensions. So now the multi-partite entanglement structure is going to matter, as will become clear later. But just for us, a very simple example in 0 dimensions. The anomaly here means projective representations. So for example, let's consider 2 spin half states with joint SO3 symmetry, the SO3 acting in the usual way. The singlet state of these 2 qubits is the only symmetric pure state under this joint SO3 symmetry. And why is that? Well, I guess you can just, I don't know, brute force, but the perspective I want to push is that the reason why is because the spin half is a projected representation of SO3, and that's the anomaly in this case. And that implies that all symmetric states are entangled. So just to review, what we mean by projective is that, okay, I have, let's say, these 2 systems, the left and the right qubit, and the symmetry action just on the left is a group homomorphism acts as the way we expect up to this phase omega of GH. And if this phase cannot be trivialized, we say it's projective. Okay, so how do you prove this entanglement property? Well, the proof is similarly to what I showed earlier, it's by contradiction. So assume there was a tensor product state, so a state of no entanglement, something on the left and something on the right, that was symmetric with this SO3 symmetry in this way, right? So let's assume that. some eigenvalue lambda of G, then, well, because it is separable state, then if I just add UL, say U left, on the left state, I also get the left state back with some eigenvalue. And same thing for the right, where the product of these eigenvalues have to match the one above, right? This is just because both the symmetry and the state are tensor product together. But then, if you just plug these relations back into this formula here, you get that this phase is what? Is this product of this phase eigenvalues here for G and H divided by their product. So which means that if you redefine this symmetry action UL to get rid of this phase mu L, then actually you can trivialize this projective phase here omega, which means that in fancier terms, which means the cohomology class of this omega is trivial, which would mean that SO3 representation spin half is not projective, which it is. So that's the contradiction. So yes, any question on this proof here? I'll basically just reiterate on this same line of arguments later on. Right. So this example in 0D, just 2 qubits, is actually what happens at the boundary of a 1D symmetry potential topological system. So it's the same idea. But now this entanglement is mediated by this entire chain if you have a boundary. And one example of that is the ZXZ or the cluster chain. So you suppose you have this Hamiltonian here with terms ZXZ. And I have open boundary conditions. So yeah, from I equals 2 to L minus 1. This system has some symmetry generated by X acting on odd sides and 1 by X on even sides. And on the ground state subspace, using that the ZXZ is 1 is a stabilizer state, the symmetries actually can be made to only act at the boundary. And importantly, the anomaly here, which is the non-trivialness of the SPT as well, can be seen by the fact that even though these symmetries commute, if you just look at the left part or the right part, they anti-commute. So you have the same story as the previous slide, where you have a projected representation if you just look at one of these boundaries separately. And so you're also going to get that if you impose these symmetries to be strong in your state, then you are going to have some long-range entanglement between the two ends. In this case, it's bipartite entanglement. Now, if you go up one dimension to 1D, another example, a simple example, is this qubit chain with the anomalous Z2 symmetry generated by the falling operator. So the symmetry here I'm considering is the part of X, so the usual Z2, but also have a part of CZ gates, control Z gates on adjacent sides. The idea here is that you basically just have a spin flip, but you twist it via non-trivial phase factor, given by this part of CZs. This is the symmetry that you have at the boundary of the 2D bosonic Z2 SPT, the Levin-Good state. And in the same way that for 0D anomaly basically means projectiveness of the symmetry, in 1D anomaly symmetry, the anomaly basically means that the symmetry is not on site. It is also not on site even if you conjugate by another local unitary channel. So same thing here. So you cannot get rid, you know, localize CZ factors to something that is on site. Right. So now the claim is similar to the one above, but now it's for tripartite entanglement. So it means if you have a pure state that is symmetric under the symmetry U, then this pure state cannot be written as a tensor product of A, B, and C. And why I'm considering pure state here and not just a generic mixed state, right, with strong symmetry? Well, that's because of the inheritance property again. If I have the proof for pure states, then I immediately also have a proof for mixed states with the strong symmetry. So the proof is as follows, by contradiction again. So assume ABC was symmetric under this U. Now I just take an inner product of a suitable Z basis product state that has non-zero overlap in A in such a way that now I get an equation over just B and C. So I imagine this ring here, so periodic boundary conditions. I have a tripartition A, B, and C. I basically remove this region A by this inner product over this equation on A. And I get a new unitary UBC that is also a symmetry of B times C. And importantly, this UBC acts in the same way as my original symmetry U in the bulk of BC, but the boundary, it doesn't act in the same way. in particular, no matter how you do this restriction, uh, you're gonna get that the square of this BC, which otherwise the square of U is just 1 because it's Z2, they're gonna be something appearing at the boundary. They're gonna be these Z operators at the boundary. And that's the anomaly. So now how to proceed? Well, similar fashion. Now you have two operators, the tensor product over something on B and something on C. B, C are separated. So the Z only acting on B is also a symmetry of my state. But then this contradicts with my original assumption, right? Because now ABC is symmetric by ZB and also U at the same time. But ZB, this B, oh, sorry, I didn't say, but it's just a side at the edge of this B region here with A. They anti-commute ZB with U, which cannot happen if they are both symmetries of the same state. So you see that the anomaly is basically still also this anti-commutation relation of these boundary operators that appear. So we've proven that no state can be tripartite separable, and the same way I'm not showing all the argument, but we can also prove that all states with the strong anomalous symmetries are long-range tripartite entangled as well. We can also make it long-range. Okay, something interesting that you can do with this result
So
is then,
sorry, Leo. In the previous slide, I kind of get the argument, but how come tripartite is important here? Is it because you have you need ZB, ZC to act on different product states, and
exactly.
but it kind of feels like that you're not using that fact, right? Like because here you just need that U and ZB anti-commute.
Right, yeah, yes, right, very, very good, very good. So I'm using the tripartition here because, okay, so for the proof, I need to remove one region, in this case A, to get the ZZ appearing. And now to complete the argument, I need to separate B from C on the state level. That's just because there's no contradiction on having ZZ being a symmetry and also U, because ZZ and U commute. But so I need to be able to show that a single Z is also a symmetry of my state to complete the contradiction. And for that, I need these like B and C to be unentangled.
Okay, I see. I see.
Right.
So because okay. So you basically acts on after removing A, right? So this UBC acts on, the union of B and C, but you need an
Exactly.
operator which only acts on B or only on one boundary of U or one boundary of B union C.
Exactly. Exactly. Because only when you have one of them that you can see the anomaly. Exactly.
So because I know this H3 construction from Czech homology, but maybe this is related because tripartite partitions are also showing up there, right? Do you know?
Yeah, actually, I'm not sure if I know what you mean.
Okay, it's just another
Yeah,
argument to essentially get the same classification, but you're kind of using an argument that's kind of different, but they should be related.
okay, yeah, I'm interested in that. Yeah, maybe let's chat afterwards.
Okay, yeah, sounds
Yeah,
good. Yeah.
yeah, interesting. Yeah, as far as we know, this argument for the tripartition first appeared here, but it'd be interesting to see if it appeared elsewhere as well.
Yep. Thank you.
And another thing you can ask is, well, okay, maybe you just shown that this proof doesn't work for my bipartite case. Maybe it's just, I don't know, not smart enough. And maybe you can also show that you have bipartite entanglement always. But actually that's false. So you can find explicit state, which is say GHZ on A and GHZ on H complement. If you choose the GHZ states right, then even though if they are bipartite separable, it's just a tensor product of two GHZs, this whole state is symmetric under the CZX symmetry. So actually this would be important right now. So another state you can consider is maximic states constrained by anomaly. So this state here is one, it's just a projection into the CZX symmetry being +1 or -1 up to a normalization. Alternatively, you can think of this as just the infinite temperature thermal state, but you're in the canonical ensemble, so you fix the charge to be +or -1. right? And I guess yet another way to view this state here is it follows the following story. So suppose I give you a gift, right? And since we're all quantum physicists, this is a quantum gift. And then I tell you nothing about what's inside. I don't ask you to not open it because it's very fragile. It's quantum. But the only information that I tell you is that it has a CZX anomaly. And I also tell the charge as well, let's say. Then what state should you have in mind? Well, it's exactly this state, right? You just know one piece of information, it has a CZX symmetry. So the state you just know is a maximally mixed with that piece of information. So it's basically one of the simplest states you can consider uh, with this symmetry. But importantly, it does have this strong anomalous symmetry. So from our argument earlier, it is long-range tripartite entangled. But at the same time, using this case-for-proof 2GHZ constructions, I'm not showing here in detail, but you can prove that it is a mixture of bipartite separable states. So itself, it is a bipartite separable state. And actually, this is something that only happening for mixed states. For pure states, if you have, let's say, tripartite entanglement, they also have bipartite entanglement as well. But for mixed states, you don't have. So using these two properties at the same time, which are almost contradictory, look contradictory, we can prove that this state is necessarily an intrinsically mixed phase of matter, defined earlier. So what I mean by that is that in this phase of matter where this state sits, there's no pure state in there. And basically the idea is because if there were, there would be a pure state that is tripartite entangled by bipartite separable up to short-range entanglement, which cannot be true. So as far as we know, this is the first like definitive example of a state in this intrinsically mixed phase of matter in the strongest sense of intrinsically mixed. All right, I'm gonna just go fast here, not very good of time. So you can extend this argument to higher dimensions for symmetries of this form here, which is basically a phase factor and a shift, also just like X and CZ. This restriction is not very restrictive because it contains all representatives in the group cohomology classification of anomaly. And well, the proof is similar. So now consider in 2 dimensions, you want to prove it's four-partite entangled. Like say this particular four partition here in this A, B, C, D regions, same thing. By contradiction, let's assume it's A, B, C, D. Now you do something you restrict to just B, C, D. Then this restricted unitary, because of the anomaly, it is the same as the original one. But if you look at the algebra defined by it, is the same up to this. Now it's on a phase, but it's an operator that act on this entire 1D boundary of BCD. Then this boundary operator act on BCD is also a symmetry. And now you just repeat the 1D proof. Now, because now you're going to get some symmetry operator, leaving 1D boundary. You have a tripartition, so it's the same thing 1D proof. The only difference is that you depend on G and H. But you still get contradiction. Now you're going to get at the 4th cohomology class. It needs to be trivial for this to happen. You might ask, okay, what happened?
If I consider anti-unitary symmetry, can I still do it?
Very good, very good. So anti-unitary symmetry is basically you cannot define strong symmetry for anti-unitary symmetries. That's yeah. That's basically because if you have anti-unitary symmetries, you don't have complex vector spaces that are stabilized by the symmetry. You have just real vector spaces. So things get messy there. I believe there is still a way to talk about anti-unitary symmetries by superselection. If there's time, we can talk about that. But yeah, strong symmetries is in principle not well defined for anti-unitary symmetries.
But I
Yeah, I
think
guess
in rather high dimensions, there can also be unitary symmetries that have anomalies not described by group cohomology.
right. Yes. Yes. So we don't know what happens there. Yeah, we don't know what happens. In fact, there are other problems about higher dimensions. It also depends on what is this four partition that you choose. Yeah, it's more subtle. Maybe just for the case of anti-unitary symmetries, just not to be like very vague. So for example, consider anti-unitary, let's say time reversal, where t squared equals to -1, right? Suppose and I'll suppose there is a side, there's an eigenvector. I'm just basically just using the Kremers doublet like argument. So if t psi is equal to lambda psi, if I add with t again, I'll get some minus sign and I get a contradiction. So basically, because of this problem, strong symmetries are not well defined.
I see.
Right. So you may ask, okay, what happens if higher form symmetries in higher dimension, or the most general case? This is the conjecture we have. So okay, so now you have anomalous symmetry, anomalous system in d dimensions. If we look at d+1 dimensions, the anomaly can be cancelled by an SPT bulk. And suppose that the effective response action of this gauged SPT bulk is of this form here. So you have these AIs here, these gauge fields. And this can be like higher form gauge fields depending on the code chain, the order of their code chains. Then the conjecture is that any strongly symmetric mixed state in this anomalous boundary has long-range k-partite entanglement, where k is calculated of this form. It just counts how many gauge fields you have in the SPT action. So yeah, it cannot be stochastic local channel acting on a mixture of tensor product over k regions. So evidence for that, for the case of p equals 1 and d equals 2, that's the one from anomaly case of topological order I just told you. If you plug these numbers here, you're going to get k equals 2, so bipart entanglement, check. Makes sense. SSP, the usual SSP, you can also view it in this way. So you just consider a 0 form anomaly, that's your symmetry, and a D form anomaly, that's just your 2-point correlation function, right? If in the case where its equation value is equal to 1 exactly. Then you also, if you plug there, you get k equals to 2, which makes sense. If you have long range order, you have bipartite entanglement. If p equals 0, you have 0 from anomaly, as we said, if you plug in z plus 2. And you can also mix between 0 from and 1 from anomaly. Here on the right is one example of that. I'm not going to go into detail, but basically you can consider a 2D system where I have x acting on one sublattice, x acting on another sublattice, is 2z2s. And for each curve, I have a string of CZs here. Then for a similar region for the CZX case, if I have an open string gamma of the CZ and a conjugate of X on one sublattice, I get Z's appearing. And these Z's appearing are going to enforce me some entanglement. In this case, it's tripartite entanglement. So it's very similar to the proofs that I've told you before. Right, so some summary and sorry for being 10 minutes late. But yeah, also it proved that anomalies implied as long-range multi-party entanglement for mixed states. And this explains the decoupled transitions as actual phase transitions and provides this novel intrinsically mixed phase of matter. Some open questions. So we've been thinking of how to generalize these consequences to non-invertible symmetries and what interesting features you have there. I also think of how to prepare some of these states in quantum hardware to try to see this entanglement, observe it. And for that, we to think about witnesses of this anomalous entanglement. So some kind of operator linear in row, whose a special value can tell you whether it has this anomalous entanglement or not. Just some directions we're looking for. And yeah, let me stop here. So yeah, you tell me if I have more time or not. Sorry, I'm already being late. I can talk more about the non-anomalous case, but yeah, if you guys want to leave, that's fine as well.
Maybe because of the limit of time, let's just stop here. But this is a really beautiful and interesting talk. Thank you very much, Leo.
Yes, thank you.
Do people have further questions?
Yeah, I do have like some interesting questions that I think at least that you will find interesting. But yeah, this is a very nice talk. Thank you, Leo. But just in the previous slide, I really like the slide that you had. This slide is very nice. It's because you've written down like this SPT that you had, and you constructed like essentially the anomaly polynomial that you want this SPT to have. But the thing I want to kind of bring to notice is that you only use the cup product, but in cohomology, you have higher cup products, right? And this is actually related to the question about Bromian rings that I had before, because the higher cup products are actually crucial for detecting well, you can't see me, but it's crucial for detecting braidings and linkings of higher form, higher dimensional membranes, let's say. So and you can actually construct like these triple Massey products in cohomology using higher cup products. So I'm just wondering, like, let's say I construct maybe it's not SPT, but let's say I just write down an anomaly polynomial using, let's say, cup one, which, for instance, eats like a P form, and then it eats a Q minus one form. So then P plus Q is equal to D plus 2 or something like that, right? Or do you think it's like this conjecture still holds? Like it still has long range entanglement?
Right, yeah. So I guess to really answer, I have to know more about these higher cup products. But maybe one thing I can tell you is a sketch of the argument that we have for this conjecture.
Right.
Maybe that elucidates. So the idea of the argument here is by dimensional reduction, um, which is similar to this argument here. Basically, having these symmetries, and then you're trying to reduce to the boundaries of boundaries of boundaries until you get
Mm-hmm.
to the
Mm-hmm.
zero form case, where you just
Mm-hmm.
piggyback to the proof we have right now. So this is the following. Suppose I order this, let's see if I remember, if this P form such that this PK here is the largest one, so you actually the smaller submanifold. Then I just it is a restrict the action on this submanifold where this AK symmetry acts. Now this guy becomes zero form there,
Mm-hmm.
right? If I choose the sections right, then the formness of all other symmetries when I reduce to this submanifold, it is still the same. I did not normally see the same. So now just proceed by just cutting these PKs, these PIs to zero,
Mm-hmm.
and then I just go to the zero form case.
Mm-hmm. Mm-hmm.
That's basically the proof. I think this argument is so well known in other cases. So yeah, I'm not sure. I guess I ask you, do you think that would work?
No, I mean, like what you described is essentially you're ungauging like the top dimension operator, let's say, or the ungauging the top dimensional symmetry, and then you do it step by step. That's right. That's right. I understand that. But like if you have cup one, let's say, then you kind of have to. Well, I don't know how it works in that case because I haven't seen anybody like construct, this k-partite partition, whatever for those things. But what I would hazard a guess is that you have to kind of jump by two dimensions at the same time. So,
Mm.
but I can't guarantee that, of course. But there's definitely some like very interesting things or very interesting topological orders that you can construct by just writing down like using higher cup products or even just cup one, like using just cup one, you can write down like ARF, for instance. So
Mm. Yeah, so yes, that reminds me, you probably know this better, but this is not the most general form you can have your gauged action in the SPT. You can also have like say if Stifel Whitney terms appearing and
right.
stuff like that.
Mm-hmm.
So we also don't know what happens in that case.
Mm-hmm.
Yeah. Yeah, that's pretty interesting. I'm interested to see
Yeah,
that.
there was this very nice kind of a review article uh, by someone I forgot, but it's a review article about higher cup products and kind of its relevance for like topological orders and stuff, which I can just send it to you later.
Yeah, that'd be great. Yeah.
Okay, but just to also go back to the argument that we were discussing about like this, like your argument about this tripartite partition, which is like the argument I'm seeing is that indeed I give you a tripartite and then I remove A and then see you know the other the operator acting on the other two bits. But then I consider the relationship between UBC with UAB and UAC. Have you seen that? Like,
Right, I guess, yeah, I can imagine that. I guess right. Right, also gonna get some trivial relations, right?
Yeah, yeah. So that's kind of like the check homology construction. And I can like the reason that you say you have ZB and ZC, ZB kind of lives on AB, and ZC kind of lives on AC. So you know it's that I think the two arguments should be like kind of they should be the same. Yeah.
Right, yeah. It seems like it's another way of like expressing the
Yeah,
anomaly.
yeah. Exactly,
Right.
exactly.
Yeah. Yeah, it's interesting how, I don't know, let's say in this case it requires three, right? Three guys. If just two, you
Exactly.
cannot.
Yeah.
That's the same reason why you have three here appearing. Yes.
Yeah. Okay, good. That's it from me. Sorry for taking up all the time.
No, thank you.
Leo, just to make sure one thing, for this high dimensional examples, you said it's D plus 2 parted, right?
Oh, right, yes, for the zero form anomaly case. Yes. Yeah.
And you show this only for high dimensions. You argue this only for exactly solvable models or for generic states.
Right, yeah. So we argue, more specifically, we argue for states whose symmetry is of this form, right? Or via this invariance of the symmetry pullback or dressings of that. The dressing by conjugation. So just to repeat, this form is basically so this part here is alpha, G alpha is on-site modification of choose a basis like alpha. Just modify on site, just like poly X, let's say, and you give this you have a phase factor, this functional, local functional, depending on G and alpha. So that comes from the Alcidiac argument actually. So there they also to make the argument work, you also could just consider these symmetries.
But is this the most generic symmetry?
Yeah, so for group cohomology classes, there exists a representative with all group cohomology classes with a symmetry acting this way. I believe for all dimensions. Yeah, so this was
I mean,
proven
suppose
this
I
way.
consider in D dimension, suppose I consider general quantum singular automata. Suppose there's no, for simplicity, and let me just consider general finite depth quantum circuit. Is this kind of, is the symmetry action written on the slide a special case of a general finite depth quantum circuit, or it somehow represents all of them?
Yeah, so this guy here would be as a circuit would be basically the CZX case. You have something X on site and some phase factor that is this local.
But this is a very special circuit.
Exactly. Yes. So yeah, we just considered these guys. Let me maybe say why you could just consider this. Is basically because it's in this step here. So it was restricted to BCD, and now we want to get this anomaly affected. So this omega, this operator, to be able to continue the proof, you want this omega to still be, let's say, a finite depth local unitary. right? And they just continue. But there's in principle no guarantee of this. I also don't have a counterexample in mind, specifically what this doesn't happen, but in general we cannot guarantee. Actually, we cannot even guarantee that it is like if this U is a quantum circuit, that this also be a finite quantum circuit. It could be that it goes to a translation in principle. We just know that it's locality preserving. So yeah, the issue here is guaranteeing that you look at the boundary anomaly, you get something that is still well behaved.
But recently, there's a paper by Cal Cawago and Weber Shirley on defining the anomaly of a 2D finite depth quantum circuit. In principle, one can take that definition and see if I consider any anomalous symmetry defined in their way, whether this argument can be whether this result for mixed states can be generalized.
Right. Yes. Yeah. Yeah. To be honest, I'm still getting grip of these recent works, but for sure, yeah, I think it'd be an interesting direction.
And also, another comment I mentioned before about the high form symmetry is you were assuming that SAB and theta defined in your way are phase factors. In general, this doesn't have to be the case, right? If you just have two one-form symmetries and you let them intersect at a certain point, uh, I mean, whether this is a phase factor needs to be proved. If we assume it's some kind of a topological state and we assume the description using topological quantum field theory, then they are phase factors. But now where you at a we're considering a lattice system, and at the lattice scale, this being a phase factor is something that we need to separately prove.
Right. You mean that you say that this at a lattice scale is like a UV detail that
Yeah.
it's not clear if it's a phase. Yes. Yeah. So do you have any specific example in mind where this doesn't work, or you're just like generally concerned?
Like one, there are ways to unambiguously find this phase factor. For example, for self-statistics, one uses the T-junction. That's kind of like the thing you did, but it's made in a
Exactly.
more
Yeah, this diagram is basically just a T-junction, but I also have another piece going upwards. But yeah, that's the idea. Yes.
yeah. Is it basically the T-junction, or is it the same as the T-junction?
So yeah, so the T-junction, so let's say look at this bottom figure here, this 3D one. You just remove one of these legs going from P to S. Hopefully one
Uh-huh.
of these guys, this is exactly the T-junction, right? Because you have one, yeah, I have one going like this, the other
Yeah.
one going like this. Yeah.
What I can say is, if we do use the T-junction, one can unambiguously find this phase factor. Now with this additional leg, maybe I'm not entirely sure. One can actually prove using the T-junction there must be the phase factor. The simplest case was proved in my paper with Rui Zhi about the K-type model in one appendix. It's a very general proof for any Z in one form symmetry. And last month, there's a paper by Xinse Liu and Yuan Chen, and they proved that they generalized this argument to more general lattices.
So let me just make sure by proving that you always can define this phase factor, you're saying that for any
So the statement
yeah.
is, on the lattice, let me define one form symmetry to be the following thing. First, uh, uh, it's defined on some say loops, and on different loops, this symmetry is commute. That's one condition I want to satisfy. And another condition I want to satisfy is if I have multiple loops. So for each loop, I have this symmetry operator. Now, if I have multiple loops together, I can multiply these symmetry operators together, right? The key requirement is that the product of this multiplication is only supported on the boundary of the bigger loop. So in general, if we multiply many loops together, The support of the product will be the whole area that is covered by these loops. The key requirement here is that in the middle of the area, there's nothing, and only the support is really on the boundary of a big loop. It is this property that allows us to say that these symmetries are living on loops. Then, assuming these two properties, and in the context, we consider that was a paper 2 years ago, on Decohered models. One can show the T-junction will necessarily generate a phase, and this phase is unambiguous. Also, it has some discrete nature, so it's some universal phase. It's all shown at the lattice scale.
I see. Interesting. Interesting. Yeah, I wasn't aware of that. So, I believe the second property. Yeah. So, yeah, I believe I'm implicitly assuming both properties here. Yes. Yeah. Yes. I'm assuming both properties. Yeah. So I guess what I mean by, especially the second one. So what I mean by high form symmetry in this case, one form of symmetry, let's say, is an operator that is supported on this line plus some width. So I already have this property. Let's say if I multiply them, it's only also going to be supported about the union of these curves up to some width. And the fact that they are, yes, and I guess also, I mean, yeah, I'm also assuming that the closed loops are a commute. But yes, very interesting. So I didn't know that just from that you can prove that these things always hold. So I guess I was also assuming, further assuming that if you do this diagram, if you look at the change of order of its operators, you get this phase. This is really an extra assumption, which I guess you can verify for specific cases, right? Yeah, so I guess the short answer is, yeah, I am assuming that these things work. This is not something that is derived. Yeah. Yeah, which I guess our main goal was to prove something about a toric code. So toric code is just X and Z's. These things work perfectly, right? And also, I guess not only for the toric code, but also dressings also work perfectly. So that'll be our goal. But yeah, interesting to see that. It's more complicated in general.
Yeah, that's all the questions I want to ask.
Yeah, thank you.
If there's no more question, I'd like to thank you again for the very interesting talk. Thank you. Okay,
Thanks.
bye.